Okay, Assalamu alaikum students, and I hope you will all fine and you are taking care of yourself. You know that this is the Zimmel's Chemistry channel, and in this channel we discuss chemistry with fun. So let's start. Bismillah Rahmanir Rahim. So in this video I will talk about for grade matric. You know that I have discussed the two topics of grade 9, and now today I will discuss grade matric first chapter, that is chemical equilibrium. So let's start. In this video I will like to cover the following topics, that are chemical equilibrium, reversible and irreversible reaction, dynamic equilibrium, macroscopic characteristics, law of mass action, derivation of equilibrium constant, and equilibrium constant and its units. First of all, I would like to discuss what is chemical reaction. You know that the reaction in which new product is formed. For example, if two species are reacting to each other, then they will form a new product. For example, if you are mixing water and sodium chloride, then there is no new product, only there will be the solution of sodium chloride, that is also known as common salt or table salt, that we used in our daily life. But in chemical reaction a new product is formed. For example, when iron will react with iron fillings will react with the sulfur, then when we heat together the mixture, then we will get the new product that will known as iron sulfide. Okay, but when we mix it thoroughly, then no new product will form, only upon heating the new product will form. So the chemical reaction is a reaction in which two species react together and form a new product. So this statement will be referred to as the term of chemical reaction. So here in this chapter I will discuss a type of reactions. We have two types of reaction. First one is reversible reaction and second is irreversible reaction. Reversible reaction means the reactions that never goes to completions. Means if the two species are reacting to each other and forming a new product, then if the product is more in the concentration, then it will go towards the reactant side. For example, if new product is forming, but if the reaction is reversible, then product can also go towards the reactant, product can also form the reactant. So when there is a reversible reaction, then there will be no completion of the reaction, but only the product and reactant will change with time to time. So it takes place in both direction, forward or backward. Forward means when reactants are reacting each other and forming a new product, then this type of reaction will be known as forward reaction. Okay, and when the concentration of the product is increased, then it will like to go towards the backward direction. Backward direction means the formation of reactants. Okay, so for example, the conversion of water from liquid to solid and from solid to liquid. This is the example that I have written from your book. So you can also follow this example in your book. Okay, so when we freeze the water, then it will form an ice, and when we will melt the ice, then water will come. So as you can see that in this type of reaction, water is actually converting into the ice and ice is again converting into the reactant, that is water. So these type of reactions are actually covered in the portion of reversible reactions. But what about irreversible reaction? As you can see from the name that irreversible is the opposite word of reversible reaction. So it's mean that these type of reaction will be opposite to the reversible reactions, like the reactions that always goes to completion. For example, as I have told you that when iron filling react with the sulfur, then it will form upon heating the iron sulfide. Then iron sulfide is actually complete reaction, it will never convert again into the iron and sulfur, okay, upon cooling. Okay, so these type of reaction in which product cannot convert into the reactants are actually covered in irreversible reaction. So it takes place only in one direction, that is the forward direction. For example, the corrosion of iron. Can you prevent the corrosion? We can prevent the corrosion of iron, but if it is once completed, then we can't do anything. Okay, before using that iron we can prevent it, but if the corrosion of iron has been taken place, then we can't do anything after the corrosion of iron. So these type of reaction are actually covered in the irreversible reaction. Now let's come towards the next slide. Okay, in this slide you can see that here they are talking about the reversible reaction as well as the dynamic equilibrium. So as we know that a reaction which never complete and exist in forward or reverse direction, such as conversion of ice into water by melting and conversion of water into ice by freezing, is an example of reversible reaction. You can see this change of state by reversible reaction in this picture, how the water is converting into the ice and ice is converting into again in water. So now let's come towards the dynamic equilibrium. What do you mean by the dynamic equilibrium? After certain time, the concentrations of reactants and products become constant, and this state is called as dynamic equilibrium. For example, you have 100% of reactants. After some time, reactants will react together and form new product. When the product is 50% and you have 50% of reactant, then there will be no change or no conversion of the products into the reactant, because the concentration of the products and the reactants are now at constant ratio. For example, but if you have 60% of the product and 40% of the reactant, then what will happen? If you have more product, then it will again start to convert into the reactants. But if you have more reactants, then what will happen? The reactant will start to convert into the product. So but when they have equal concentrations, for example, product is having 50% of the concentration and reactant is also having 50% of the reaction of the concentration, then it means there is a now you can say constant equality of the concentration is actually the you can say constant becomes, their concentrations becomes constant, because now no one of the species is at the higher concentration. When both of the species reactants and the products have the constant concentration or equal concentration, then there will be a state is occurred which is known as equilibrium, or we can say it as dynamic equilibrium. So dynamic means constant concentrations of both reactants and products. In short, we can say that the rate of forward reaction in which the product is forming and the rate of the reverse reaction in which the reactants are forming, so these rates will be equal to each other. Now let's discuss the graph. In this graph you can say that we have taken concentration mole per decimeter cube on the y-axis and time on the x-axis. You know that what is an x-axis and what is a y-axis. You can see that reactants, they want to show you that with time to time the reactant concentration will start to decrease. Okay, why? Because when reactants react together, their concentration will start to decrease, then your product will start to make na, and or then your product will start to form. So when the reactants react to each other, their concentration will start to decrease and they will form the product. As you can see that product line is showing that with time to time, when your time is increasing, your product formation is start to increase. And you should know that in the starting the product formation is actually higher. Product will form as quickly as so. Okay, in the starting the product concentration will start to increase quickly and reactant concentration will start to decrease quickly. Okay, so you can see this in this diagram or in this graph. After some time, both of them will be constant to each other. The concentration will be equal, you can say that, or their concentration will not react more towards each other. So when this type of condition occurs, you can say that this is a constant concentrations at equilibrium. Now their concentration is not changing with time to time, so this type of condition is known as constant concentrations at equilibrium. In a reversible reaction, dynamic equilibrium is established before the completion of the reaction. Okay, when the reaction is not completed but the concentrations are actually on at constant, so that's why they will never form more product or more reactants. Then at this condition the rate of both forward and reverse reaction becomes equals upon reaching the equilibrium point. The following graph is which is of concentrations versus time shows that the concentrations of both reactants and products becomes constant with time to time at equilibrium. So this type of state is known as equilibrium or dynamic equilibrium. Okay, now let's move towards the next page of your book. On this page they want to share an example. An example of a reaction at equilibrium is a reaction of hydrogen and iodine. Here they are saying about the reaction of hydrogen and iodine in a closed container. You know that hydrogen belongs to group 1A and iodine belongs to group 7A. Hydrogen needs one electron to complete its outermost shell, whereas iodine needs only one electron to complete its outermost shell, because iodine have 7 valence electrons, so one electron is needed according to the octet rule. I know that you don't know about the octet and the duplet rule, so here I would like to share the information about the octet and the duplet rule. In duplet rule says that when we have 2 electrons in the valence shell, then the atom will be stable. For example, this stands for hydrogen, because hydrogen and helium. Why? Because both of the elements actually have very less number of electrons, that's why they both follow the duplet rule. But what about the iodine? Iodine actually belongs to the 7A group, so it's mean that it will not follow the duplet rule because it have more electrons. So when we have more number of electrons in any atom, then it will follow the octet rule. Okay, so in octet rule it says that when there are 8 electrons in their valence shell, then the elements will be stable. So both of the atom needs one electron. So iodine and hydrogen will form the covalent bond. They can't form ionic bond, because in ionic bond there is a transference of electron, complete transference of electron, but both of them needs one electron, so they will share their electrons. Okay, so in a closed container to produce hydrogen iodide, what will happen at the start of the reaction? You know that there is high concentration of reactants at the initial state. Why? Because at the initial state there is no reaction, so that's why there will be the high concentration of hydrogen and iodine, and after some time what will happen, their concentration start to decrease. Why? In order to form the hydrogen iodide, the product. Okay, so the concentration of hydrogen iodide increases as the forward reaction proceeds. As hydrogen iodide is formed, the reverse reaction is then able to occur. When we have a maximum concentration of product, then it will start to go towards the backward direction or to form the reactant side. As you can see that first hydrogen and iodine will react to each other, and then they will form a product that is known as hydrogen iodide. When hydrogen iodide is formed at high concentration, then it will start to decrease its concentration by forming the reactants as hydrogen and iodine. As you can see that in the flask, what is happening, round bottle flask, you can see that first hydrogen and iodine is reacting, and secondly it is forming hydrogen iodide, and in the last it will again start to decrease its concentration. So there is no observable changes, although both forward and reverse reactions are occurring. The reaction has not stopped but reached dynamic equilibrium. It will not stop but reach dynamic equilibrium. As we have discussed this term dynamic, what is dynamic equilibrium, in the previous slide. So let's move towards equilibrium in our body. Okay, now let's discuss this slide, equilibrium in our body. Equilibrium is actually present in our bodies. You know that hemoglobin is actually the macromolecule. What does hemoglobin? It transports the oxygen around our bodies. If we have no oxygen around our body, what will happen? We would not survive. So the hemoglobin has to be able to take up oxygen but also to release it and this is done through changes in the chemical equilibrium of this reaction in different places in our body. So equilibrium in our body is actually related with the hemoglobin. Okay, so you can see that how hemoglobin is performing the chemical equilibrium in our body and how much it is important to our body. So now let's move towards the term equilibrium. What is equilibrium right now? We have discussed many examples of equilibrium. We are discussing the term equilibrium. Equilibrium means the state in which the forward and reverse reactions are equal, which is known as equilibrium. Okay, so it is just like the dynamic equilibrium. It means chemical equilibrium depends upon the reversible reactions only. It's mean we can only discuss the reversible reaction in equilibrium. Why? Because it is actually concerning with the rate of forward and backward direction that is actually involved in only reversible reactions. Okay, so this is the equilibrium. Now what is the way to write the reversible reaction? As we have discussed that these type of reaction will never go towards the completion. First of all we will write the forward reaction. In forward reaction you have to write the formation of product. For example, in this reaction nitrogen gas is reacting with the hydrogen gas and forming the ammonia gas. So this is the forward reaction in which you have to notice the shape of the arrow, the arrowhead. Where the arrowhead is standing, you can see that where the product is forming. So here you have to show the arrowhead. So what about the reverse reaction? When the arrowhead will be towards the reactants. Why? Because now the product is decreasing in its concentration and forming the nitrogen and hydrogen gas. When both of these reactions are written together as a reversible reaction, then we have to make the both of the arrows, formation of the product side and formation of the reactant side. So this is the way to write the reaction of reversible. Okay, now these are the example and you have to write the forward and reverse reaction for the following. Okay, reverse means backward reaction. Sometimes to show the reversible reaction we make the half arrow. Okay, as you can see in this picture. So but what you have to do, you have to write the forward reaction. For example, what will be the forward reaction for N2 plus O2, reverse reaction to NO? The forward reaction for this equation will be N2 plus O2 arrow, first arrow that we have that is actually shown to you in this first, you can say in first picture. So this arrow you will form and you will show 2NO. Okay, and for the reverse reaction you will show the backward reaction. Okay, you will show the backward arrow. Okay, so this arrow will be shown. Okay, so write by yourself. I think you have written. Okay, now let's see what I have done for you. Okay, by this way you have to write the forward and reverse reaction of the other two equations. Okay, so in this slide I will like to discuss some characteristics of the dynamic equilibrium. In dynamic equilibrium, first of all you should know that it only exists in a closed system. Okay, and at equilibrium concentration of reactants and products remain constant. At equilibrium the forward and reverse reactions are taking place at equal and opposite rates, as I have told you before. So it can approached from either side of the reaction. It can approach, you can say that it can also approach from the forward as well as from the reactant side. It can be disturbed and again achieved under the given condition of concentration, pressure and temperature. So if you have the change in concentration and pressure and temperature, then what it will be, it will be disturbed and you have to achieve it again. These are the very important characteristics of the equilibrium. Now let's move towards the law of mass action. Sometimes some students become very confused due to the law of mass action. That is very easy. Always remember that students, you have to write each and everything in the points, otherwise you will not going to get good grades or good marks. Okay, so for good grades and good marks you have to take care of your writing as well and your method as well. Okay, your method and your writing way both are very important. So now let's move towards the mass action. In the law of mass action, first of all, you should know that what is the suggestion of the mass action. The suggestion of the mass action is actually related with the dynamic equilibrium. And what the dynamic equilibrium says? Dynamic equilibrium says that the ratio of the reactant concentration and the product concentration is constant at a state of chemical equilibrium, as we have discussed it. Okay. Upon this suggestion, you have to derive an equation, or you can say that a derivation, or a relation. Okay. So first of all, we will consider an equation. As you can see that the reaction is AA, and the small a b c d is actually representing the number of moles. Okay. The number of moles are actually written before the any species. The number of moles, always we will see the number of moles before any species. Okay. So what you will do the forward for the forward reaction. First of all, you will consider the forward reaction. We are actually talking about the reversible reaction, and you know that reversible reaction starts with the reactants. Okay. So first of all, we will talk about the reactants. Okay, in forward reaction, you know that the reactants are first A plus BB. Okay, so A and B are reactants, whereas A and B are the number of moles needed to balance the chemical reaction. So the forward reaction will be represented by RF, and then we will place the proportionality sign, that actually make the relation with the other species. So you will write the square bracket, you will write the reactants by using the square brackets, and you will also mention their number of moles. Okay, you will also mention their number of moles. These are the number of moles, you can see that. Okay, so here we will place a number of moles, and we will use this square bracket. Square brackets actually shows that the species is in molar concentration. It is actually representing the concentration. Okay, so for representing the concentration, we will use a square bracket. You know that when we remove this proportionality sign, we use a constant. So here we will use the constant kf. Kf is actually the rate constant, you can say that. And f is representing, this is the forward reaction. So this reaction will be, or this equation will be, Rf is equals to Kf, molar concentration A, number of moles A. Okay, and molar concentration of B, and number of moles B. So this is the rate of forward reaction. Okay, now let's move towards the reverse reaction. Reverse reaction, you know that the backward reaction, and in backward reaction the product is start to decreasing. Okay, so we will write the, so in the reverse reaction we only consider the product. Why? Because in the reverse reaction products are the reactants, or the products, you can say that products is going to decrease. So the species that is going to decrease, we will write those species in the reaction. So RR means the rate of reverse reaction is directly related to the molar concentration of the product. C, or and we will mention the number of moles C, and D the number of moles D. Okay, so you can see that and this we will write the rate of reaction of the reverse reaction. And for this, when we remove the proportionality sign, we have to place here the rate of constant, that will represented by KR. Why? K stands for the constant, and R is representing that we are talking about the constant of reverse reaction. Okay, so now what we have to do, where KR is the rate constant for the reverse reaction. Okay, so what we have to do, you know that at equilibrium rate, at equilibrium what happens? At equilibrium, the rate of the forward reaction and the rate of the reverse reaction is actually becomes equal. Okay, so when we talk about the equilibrium, we have to write both of the rate of the forward reaction, as well as we have to write the rate of the reverse reaction, and we have to equal both rates. Okay, so we will write Rf is equals to, according to the equilibrium, Rf is equals to Rr. So what we will do, we will put the value of Rf in the place of Rf, what we have derived, by using the molar concentrations. Okay, then we will put the Kr value R value in the place of RR, rate of reverse reaction, that we have derived before. Okay, now what we have to do, now when we compare, then Kr will go towards the Kr. Here you can see that Kr is actually multiplying with the molar concentration. On the other side it will be divided with Kf. So Kr will be divided, okay, will the denominator, and Kf will be the nominator. And here the molar concentration of the Kf will go towards the denominator. Why? Because it is also multiplying here, so on the other side it will go towards the division. So for Kf divided by Kr ratio, we use the term Kc. Kc means equilibrium constant, okay, and we can say that Kc is equals to products divided by reactants. Why? Because we have taken here the molar concentration of the products, and in the denominator we have taken here the concentration of the reactant. So Kc will be equal to product divided by reactant. You can see that it is very easy, but sometimes students will get confused by listening the name of law of mass action, and they thought that, but I don't know how to drive it. But it is, as you can see, that it is very easy, and in the paper, students, you have to write in the similar way in the points. Okay, okay students, so in this slide I would like to discuss what is active mass. Okay, active mass means the concentration of the reacting substance is called active mass. Okay, so the reactant that are actually reacting to each other, their concentration is known as active mass, and the unit of the active mass is mole per decimeter cube. Okay, what is the unit of active mass? Mole per decimeter cube, and its value is expressed in square brackets. As I have told you that in square brackets we mention the each term that is actually the concentration, okay, and the unit of concentration is mole per decimeter cube. Now let's move towards the example 1. So I have told you how to write the forward reaction and how to write the reverse reaction, and what is the derivation of the equilibrium constant. So if you have an example for the reaction that is actually sulfur dioxide and oxygen is reacting to form the sulfur trioxide. Now what you have to write? You have to write the forward reaction. The forward reaction means the reactants and their concentration. So to show the concentration of the reactants, you will use the square brackets, and the coefficient that is actually written with the SO2 representing the number of moles, as I have told you that the number that is actually attached with the any species represents the number of moles. So number of moles will be here is 2 with the sulfur dioxide. So 2 will be the coefficient, and it will represent it as you can see in the rate of forward reaction. In the rate of reverse reaction, you have to write the reverse reaction. RR is equals to KR square brackets SO3, that is a product, and the 2 is written for the coefficient or the number of moles that is actually attached with the sulfur trioxide, as you can see here. Okay, so this 2 is representing the number of moles or coefficient. Okay, so the equilibrium constant will be Kc is equals to product rate of reverse reaction, or the Kc is equals to rate of the product divided by the rate of the reactant. So you have to write the rate of the reverse reaction divided by the rate of the forward reaction, as we have discussed that Kc is equals to RR divided by Rf. Okay, so this is the way to write the equilibrium constant. So this is the test that you have to take by yourself. First of all, what is active mass? I have told you the mass concentration of the reactants that are reacting to each other is known as active mass. You can also mention its unit. Secondly, you have to figure out the coefficients for given hypothetical reaction. Okay, so to solve the Kc equation, first of all you should know that what are the coefficients as well as what is number of moles. In this reaction you can see that 9 is written with the x, so 9 is coefficient. There is no value with the y3, so its coefficient will be 1. 3 is written with the x3y. 3 is the coefficient of the x3y. So you can see that the number of moles is actually the coefficients. Equation that are given to you, what you have to do, you have to write the Kc equation for given equations. Okay, you can write, first of all you have to write what is the value or what is the formula of Kc. You know that Kc is equals to rate of reverse reaction divided by rate of forward reaction, and then you will write the rate of forward reaction and rate of reverse reaction, and then you can put the values. Okay, so what is your homework? The homework is you have to learn each topic and take tests from yourself, and you have to prepare the remaining topics for MCQs. In this video I didn't explain any of the numericals, so in the coming video inshallah I will discuss the numericals that are actually covered in this chapter, as well as the remaining topics. So but you have to prepare yourself. If you have any confusion, you can contact me. You can write your question in the comment section. Inshallah I will try my best to build your clear concept about the chemical equilibrium. I hope you will learn a lot by my video. So to get more videos, follow my channel, subscribe my channel, and like my channel. Okay, so thank you so very much for your participation. Inshallah we will meet again in the next video. Okay, Allah Hafiz.